We shall now do quadratic reciprocity law, the Jacobi symbol. We have already seen these two properties, minus 1 by q equal to minus 1 raised to q minus 1 by 2. It is one property. Another is 2 by q is equal to minus 1 raised to q square minus 1 by 8. What we shall now do is, in this theorem, if PQ are odd bigger than 1 and they are co-prime, P and Q are co-prime, then P by Q into Q by P equal to minus 1 raised to P minus 1 by 2 into Q minus 1 by 2. Minus 1 raised to P minus 1 by 2 into Q minus 1 by 2. This is exactly the quadratic reciprocity law if capital P, capital Q, they are just prime numbers, odd primes which are distinct. The proof of this follows from the quadratic reciprocity law for odd primes. So, proof follows from quadratic reciprocity law for odd primes. We have to use the definition of the Jacobi symbol. The proof is like this. Write P equal to P1, P2, PR, P1, P2, PR equal to Q1, Q2, QS, where PI and QJ are primes. They are odd primes because P and Q are odd integers. They are odd primes. No Pi will be equal to Qj. Is any Qj. Because P and Q are co-primes. Since P, Q, GCD is 1. No Pi is equal to any Qj. So, use the definition of the Jacobi symbol and write the left hand side P upon Q into Q upon P in terms of the legendre symbols. Now, P upon Q into Q upon P is equal to product J equal to 1 to S. So, and now you can also at the same time P upon Q, P you can write as P1, P2, PR, and Q you can write as Q1, Q2, QS. So, this P upon Q itself you can write equal to 1 to R, J equal to 1 to S, Pi upon Qj. This is the first term, P upon Q. What about the second term? Qj upon Pi. So this is product equal to 1 to R, product j equal to 1 to S, Qj upon Pi. This is the first bracket, second bracket. These are RS terms. Here also we have RS terms. We can bring them together, this multiplied by this. And then I and j are varying. That way you can write. So this is product I equal to 1 to R, product j equal to 1 to S, Pi on Qj into Qj on Pi. We have a bracket here. What is this quantity? This quantity is there in the quadratic reciprocity law. We know its value. It is minus 1 raised to Pi minus 1 by 2 into Qj minus 1 by 2. This is equal to product I equal to 1 to R, product j equal to 1 to S, minus 1 raised to Pi minus 1 by 2 into Qj minus 1 by 2 by what? Quadratic reciprocity law. Now this can be written as product minus 1 raised to this. So this product we can remove and replace it by sum here, because minus 1 raised to a into minus 1 raised to b is minus 1 raised to a plus b. So you can write it as minus 1 raised to summation. So this is I equal to 1 to R, j equal to 1 to S, Pi minus 1 by 2 into Qj minus 1 by 2. This whole thing is the power of minus 1. Now this can be written as minus 1 raised to summation Pi minus 1 by 2 in the first bracket I equal to 1 to R into summation j equal to 1 to S Qj minus 1 by 2. But P minus 1 by 2 is equal to P1, P2, Pr minus 1 by 2 is congruent to summation of Pi minus 1 by 2 mod 2. Here I equal to 1 to R. And similarly, Q minus 1 by 2 into Qj minus 1 by 2, j equal to 1 to S mod 2. In a similar manner, these two is congruent to product of these two, mod 2. Therefore, P minus 1 by 2 into Q minus 1 by 2 is congruent to this product, summation Pi minus 1 by 2 I equal to 1 to R into summation Uj minus 1 by 2 J equal to 1 to S mod 2. Mod 2. So you see that here we have minus 1 raised to this into this. But this power is congruent to P minus 1 by 2 into Q minus 1 by 2. So if I call this as 1, we get therefore from 1 P by Q into Q by P equal to minus 1 raised to P minus 1 by 2 into Q minus 1 by 2. That is the result we wanted to prove. These three properties of the Jacobi symbol are similar to the properties of the Legendre symbol. So we will see how we can use these properties in the evaluation of the Legendre symbol. For example, let's take is 351 quadratic residue modulo 601. That is the question. So 601, is it a prime number? Should check primes less than 25. 25 square is 625. So check whether it is divisible by 3, 5, 7, 11, 13 to 23. You will see that none of these divide 601. This is a prime number. So 601 is prime. Solution. Therefore, 351 is a quadratic residue, not 601. If and only if 351 divided by 601, Legendre symbol is equal to 1. Therefore, 351 is a quadratic residue mod 01 if and only if the Legendre symbol 351 by 601, Legendre symbol is equal to 1. Once this 601 is prime, we can talk of the Legendre symbol. If this is composite, then we cannot say that. But now, when 601, because 601 is a prime number, the Legendre symbol is equal to the Jacobi symbol. Now, 351 by 601, Legendre symbol 51 by 601, Jacobi symbol. That one method of finding out the Legendre symbol was factorize this number. What are the factors? If you divide, so 3 is a divisor of this. In fact, 9 is a divisor of this. Okay. So 9 from this. So 351 is equal to 9 multiplied by 9, 39. And again you can write 39 as 3 into 13. So now what you could do otherwise was here 351 by 601 will be equal to 9 by 601 into 3 by 601 into 13 by 601. So 9 is a square, so this quantity is plus 1. Now you have to find out this and this. And 3 is a prime, 13 is a prime, so you can use the quadratic reciprocity law and we can proceed. That is the direct method using the Legendre symbol and its properties. But if you want to use the Jacobi symbol you can have for odd numbers. This is also odd. We don't have to factorize this number. You can directly 601 divided by 351. Jacobi symbol. As a Legendre symbol, this is not meaningful because this is not a prime number. As a Jacobi symbol, it is meaningful because 351 is an odd number. Now, here I have used the quadratic reciprocity law for Jacobi symbol. And capital P by capital Q is equal to capital Q by capital P. The reason for this is that this is 3 mod 4, but this is 1 mod 4. So one of the numbers is congruent to 1 mod 4. Okay. So, since 601 is congruent to 1 mod 4, that's the reason. So you can invert it and sign remains the same. Now you can use the property that if P and P dash are congruent mod capital Q, then P by Q equal to P dash by Q. So divide this by this, find the remainder. What is the remainder? It is 250 by 351 Jacobi symbol. So we could avoid factorization. Now, you cannot invert it, remember, because this number is an even number. Even number you cannot put in the denominator. So, before inverting, you should take out the power of 2 which is there, whatever it is. So, this is 2 by 351 Jacobi symbol into 125 by 351. So here one possibility is you understand that 25 is a factor of this, 25 into 5. And then you can use 25 divided by 351 is equal to 1. If you do that, that's also fine. But without factorizing also you can go ahead. Only factors required are powers of 2 you should take out. Apart from that, you don't have to find any factors. So there are two ways. This you can use 125 by 351 is equal to 25 by 351 into 5 by 351 and proceed. This is using factorization. Otherwise you can just proceed and see what happens. So what is now 2 by 351? This is actually 7 mod 8. So 351 is congruent to 7 mod 8. Therefore, what is 2 by 357? 351? That's equal to plus 1. By the property of 2 by capital Q. That if Q is congruent to either 1 or 7 mod 8, then the value is plus 1. So this is 1 into this we can invert. This is 1 mod 4, so you can just write 351 by 125 J. Here, although this is composite, you can put it in the denominator because it is odd. And this we can do because 125 is congruent to 1 mod 4. Again you divide and see what happens. This is 250, you subtract from this, so we get 101 by 125. This is the illustration I am doing it. Otherwise you could simplify it by using 25 by 351 into 5 by 351. So point is, without factorizing you can go ahead, only 2 you should take out. So now can you invert it again? This is equal to, these are both odd numbers. So we can say 125 by 101. Because both are 1 mod 4. Oh, this is what? 24 by 101. So 2 you should take out. So it is 6 by 101. Because 4 is a square. So square you can forget. This is the rule. So 2 by 101 into 3 by 101. What is 2 by 101? Modulo 8 we should see. It is 5 mod 101 is 5 mod 8. Because 12 into 8 is 96. 96 plus 5 is 101. This is 5 mod 8. So what is 2 by 101? It is minus 1. So this is minus 1 times into 3 by 101. Means 101 is congruent to 5 mod 8. It is either 3 or 5 mod 8, then 2 by that number is minus 1. Okay, so this is minus of, can you invert it? Minus of 101 by 3. This is minus of 2 by 3. 2 by 3 is again minus 1. It is plus 1. The conclusion is that 351 by 601, Legendre symbol is plus 1. The Legendre symbol was Jacobi symbol, and that we calculated. Therefore, 351 is a quadratic residue. Mod 601. For example, find out Let's say 65 by 23. 23 is prime, this is Legendre symbol. If you want to find it, you can consider it as a Jacobi symbol. 65 by 23 is prime. This you have to factorize otherwise. If you don't want to consider it Jacobi symbol, then you should factorize it. You should say it is 13 into 5. So, u by 73 into 13 by 73. That you have to calculate further. As a Jacobi symbol, you can just consider it like this and invert it. 73 by 65. Because both are odd numbers. So, whether plus sign or minus sign, 23 is 1 mod 4. 65 is also 1 mod 4. So, plus sign. Plus sign. So, plus sign because as let us say 65 is congruent to 1 mod 4. Any one of them. Now, just reduce it 5. It is 8 by Jacobi symbol. So this is 4 into 8. 4 you can forget. Because you can write it as then it's equal to 2 by 65. Because 4 is a square. It is 2 by 65. Again you have to see modulo 8. What can you say about 65? 1 mod 8. So this is equal to 1. Means 65 is congruent to 1 mod 8. You have obtained this thing. Jacobi symbol is very much used by the computers. When computers find out the value of the Legendre symbol, because computer can avoid factorization except that powers of 2 you have to take out. Otherwise you can invert using the reciprocity law. So this is how the Jacobi symbol is useful, especially for finding Legendre symbol for large primes. Okay. Now we shall see properties of the Legendre symbol, other properties. This is an example show that relation j by p, j equal to 0 to p minus 1 is equal to 0. Of all the Legendre symbols, j by p, j varying from 0 to p minus 1, this is 0. Value of j by p is either 0 or plus 1 or minus 1. When is that 0? If j equal to 0, then j by p is 0. That is the only value of j for which j by p is 0. Or j equal to 1, 2, etc. up to p minus 1, they form a reduced residue system. Value of j by p is either plus 1 or minus 1. What does this mean? That the sum is 0. It means as many ones are there as there are minus ones. Number of ones is equal to number of minus ones. Then only the cancellation and the answer will be 0. Is that true? So, just note that for j equal to 0, 0 by p equal to 0. j equal to 1, 2, etc. up to p minus 1, j by p is 1 or minus 1. How many times j by p is plus 1? You see that there are as many quadratic residues as there are quadratic non-residues. Among 1, 2, etc. p minus 1 is a reduced residue system mod p. Exactly half of the elements numbers are quadratic residues mod p we have done, right? Half are quadratic residues and half are quadratic non-residues. And the remaining half is p minus 1 by 2 elements are quadratic non-residues. This means that this sum is therefore summation j by p, j equal to 0 to p minus 1 is equal to, j equal to 0 gives you 0 plus p minus 1 by 2 times plus 1 plus p minus 1 by 2 times minus 1. Half the times it is plus 1, half the times it is minus 1 because there are p minus 1 by 2 quadratic residues and p minus 1 by 2 quadratic non-residues. This is what we have seen already and therefore this is 0 that we wanted. The similar example in summation x plus b mod p is equal to 0 to p minus 1 where if p equal to 1, b belongs to z. B can be anything, any integer. A is an integer which is coprime to p. Earlier we had j by p, then the symbol j by p and its summation. Here now instead of j I have ax plus b. X varies from 0 to p minus 1. You say something about this? That as x varies from 0 to p minus 1, x plus b, that also is a complete residue system mod p because A is coprime to p. So, for x equal to 0, 1, 2, etc. up to p minus 1, x plus b gives rise to complete residue system mod P. As x varies from 0 to p minus 1, ax plus b varies over a complete residue system mod P. Therefore, what happens is, for every x between 0 and p minus 1, ax plus b corresponds to a unique element from 0 to p minus 1 mod P. X plus b is congruent to one and only one element from 0 to p minus 1 mod P. Different elements from the set Ax plus b, they correspond to different elements from 0 to p minus 1. Okay. So this is a complete residue system. Therefore, and we know that if A congruent to B mod P, then A by P equal to B by P. Therefore, this sum is nothing but sum of terms like J by P. For every x, there is unique J, okay, between 0 and P minus 1, such that x plus B congruent to J by P. We can say, therefore, for every belonging to 0, 1, etc. p minus 1, there is unique J into 0, 1, etc. p minus 1, such that x plus b congruent to J mod P. So, x plus b by P because the numbers are congruent, therefore corresponding Legendre symbols are equal. Also, different values of x correspond to different z, or different x belonging to 0, x plus b corresponds to 1. Therefore, summation x plus b by p x equal to 0 to p minus 1 is the same as summation j by p j equal to 0 to p minus 1. And we know that this sum is equal to 0. That proves the result. You have got the value of this sum. So, this Legendre symbol is also useful in finding out the points on certain curves over finite fields. So, example, so that the number of points or y in ZP or ZP is fine. A square equal to fx. Fx is some polynomial is p plus summation x by p x equal to 0 to p minus 1. Zp means z by pz, or we can describe it as the reduced residue system mod p, complete residue system mod p. So, for every x mod p, how many y are there mod p? That's what we have to say. So, for every solution is for every x mod p, number of y mod p is fine y square equal to fx is one plus fx by p. 1 plus x mod p. Let's check this. Why is this so? So, suppose fx is a square mod p. Fx is 0 mod p. If fx is 0 mod p, if fx is 0 mod p, then fx by p is 0. This quantity is 1. Now, if fx is 0 mod p, then y square is 0, that means y is 0 mod p. That means there is only one value of y corresponding to this value of x. Now, suppose fx by p is minus 1, this is minus 1, then this value will be 1 minus 1, 0. Now, fx by p is minus 1 means fx is not a square mod p. And then y square equal to fx will not have solution mod p. Square equal to fx. Because fx is not a square of anything. Y square equal to fx will not have solution mod p. So the number of corresponding y is 0. Here also you get 1 minus 1, that means 0. Now if suppose fx by p is plus 1, then this is 1 plus 1, that is 2. Whereas here what will happen? If fx by p is plus 1 means fx is a square of something mod p. If fx is square of something, suppose fx is a square, then what is the value of y? Y can be a mod p or y can be minus a mod p. Now, if you take p to be odd prime, then a and minus a, they are different. For an odd prime p for which we are defining this legendary symbol fx by p, we get two values of y corresponding to this value of x, such that fx is a square mod p. So here we are assuming that p is odd prime. So maybe let me mention it. P odd prime. So that this symbol is meaningful. Alright, so we can just illustrate. Now, for x mod p such that x congruent to 0 mod p the corresponding y satisfying y square congruent to fx mod p is 0 mod p. value y. In this equal to 1. Now take x such that if x is a quadratic non-residue mod p. So if mod p is such that x is quadratic non-residue mod p, then there is no y such that y square congruent to x mod p. Also 1 plus x by p equal to 1 minus 1 equal to 0 in this case. If x is a quadratic residue mod p, then what happens? A square congruent to fx mod p has two solutions. P is an odd prime, so there are two solutions. Also 1 plus x by p, what is that? Is 1 plus 1 equal to 2. These numbers also match. Therefore, for every x mod p, the number of y mod p such that a square congruent to fx mod p is, what is this number? 1 plus x by p. In any case we get this. Therefore, now x is varying between 0 to p minus 1 or some residue system mod p. Hence, number of points cross zp. X is varying mod p and y is also varying mod p, in which satisfy a square equal to fx. That is satisfying a square congruent to fx mod p is, we can just this, we can just say y square equal to fx is what? Summation x equal to 0 to p minus 1 you separate this out, 1 is added how many times? P times. It is equal to p plus summation x by p is equal to 0 to p minus 1. For example, just a consequence of this, number of solutions of y square congruent to square just take simpler one, 2x plus 3 odd p odd prime. What is this? How many solutions are there for this? This is a quadratic congruence in two variables, x and y. Left hand side we have y square and right hand side we have 2x plus 3, which is linear. So by this argument, this is like y square equal to fx. Fx is 2x plus 3. This we can get as p plus summation 2x plus 3 by p. Y square equal to fx, p plus summation fx by p. Now this we can really calculate. We already know the value of this. X plus b, it is of that type. A equal to 2 and 2 is coprime with p. So since 2p equal to 1, summation 2x plus 3 by p is equal to 0 to p minus 1, 0. Therefore, number of solutions of the congruence is plus 0, so p. Example, number of solutions of y square equal to into, or I will take square plus x mod p, square plus x mod p. P is odd prime. Now, what is this number of solutions? Is number of solutions is, you can say NP equal to, number of solutions is NP modulo P. What is that? P plus summation x equal to 0 to p minus 1 is fx, y square equal to fx. So it is x square plus x by p. Now we do some trick here. First of all, x equal to 0 will give rise to 0. So we can see is, so let us just calculate that separately. Now, summation x square plus x by p, x equal to 0 to p minus 1, summation x equal to 1 to p minus 1, x square plus x by p. For every x, there is some x bar such that x bar is congruent to 1 mod p. Is x bar is that x bar. Here means x bar by p square. That is also is 1, so x bar square by p is 1. So we can multiply this by x bar square by p. Therefore, the above equal to summation x equal to 1 to p minus 1 x bar square by p, because this is 1, into x square plus x by p. So a by p into b by p is ab by p. So you multiply inside. Summation x equal to 1 to p minus 1. This into this, what is that? X into x bar is 1 mod p. So it is 1 plus x bar by p. Now put x bar equal to y. As x varies from 1 to p minus 1, x bar also varies from 1 to p minus 1. It inverses. So as x varies from 1 to p minus 1, y equal to x bar varies 1 to p minus 1 mod p. Therefore, equal to summation x equal to 1 to p minus 1, 1 plus y by p. And we can take y equal to 1 to p minus 1. Okay. This we can write as summation y equal to 0 to p minus 1, 1 plus y by p. Now I had taken y equal to 0 means 1 plus 0 by p, I had taken additional. So minus 1 by p. Minus 1 by p. It is minus 1. So, and what is this thing? This is ay plus b by p type thing, that is 0. That is 0 minus 1 equal to minus 1. Therefore, number of solutions equal to p minus 1. That is the answer. This is how the Legendre symbol can be obtained in solving congruences, quadratic congruences.